So now we're going to take our implicit differentiation to the next level, because you'll notice that we have another expression to find our derivative, our implicit differentiation this time, but you'll notice that we have a mixed xy term, and that sometimes causes a little bit of confusion. So in order to help you with that, let's go take a step back for a minute and remember our product rule, right? Our product rule went like this. We said that if we had the derivative with respect to x of a product, u times v, where u and v are both functions of x. I'm going to put this in the dx notation right here. So what we would have said was that it'd be the first function times the derivative of the second function with respect to x plus the second function times the derivative of the first. And if you need to go back and review this video right here that we had of using the product rule, you should. But we're going to use that product rule right here when it comes to this mixed x and y term. And you can imagine that what's going to happen in one of them, we're going to end up with a dy dx term. It does end up being a little bit more involved, but we'll see how this works out. So let's try this out now. We've got our derivative with respect to x of the quantity 5x minus 2xy, there's where our product rule is going to be, minus y squared. So we want to take the derivative of all of that and set it equal to the derivative with respect to x of 0. Well, the derivative with respect to x of 0 is still going to be 0. So the only real part that we're going to have to worry about is what happens with each of these terms. So we're going to end up with 5 times 1, which is the derivative of x, minus 2 times the derivative of xy. I'm just going to leave it as xy for right now so we can see this in action. Minus the derivative of y squared. And as we know from previously, we said, well, this is going to be 2y to the first, like our chain rule would say, times dy dx. Okay, so now we get to this xy mixed term, and let's see what's going to happen when we have to deal with it. In this case, I'm going to have 5 minus 2 times what? Let's see. By our product rule, instead of u and v, we've got x and y. So we're going to take x, which is our first function, times the derivative of y with respect to x. And then we're going to add to that plus, so plus, and you notice I've got a big parenthesis around here to keep track of this, plus y times the derivative of x with respect to x. And I'll fix that in a second. Minus 2y times dy dx is equal to 0. Okay, so what I should do really is distribute this negative 2 throughout and reduce this. If I take dx over dx, well, I'm taking the derivative of x with respect to x. I know that just goes to 1, right? Anything divided by itself would be equal to 1, and this is no exception. So I'm taking 5 minus 2x times the derivative of y with respect to x. I'm going to distribute that negative to the next term, so minus 2 times y times 1 minus 2y times dy dx equals 0. Okay, we've actually finished at this point the differentiation. So the derivative part, the actual implicit differentiation, is done. Right? That's a good thing for us. The next, however, is that we also have to do a little bit of algebra to isolate dy dx. So yeah, I know, a little bit more work. Let's try it out. What I'm going to do is all of my dy dx terms I'm going to isolate to one side. So I'm going to actually do it by addition. I'm going to add 2x dy dx plus and 2y dy dx to the right hand side. So what I get is something that looks like this. 5 minus 2y is equal to 2x dy dx. So I move this over by addition. And I'm going to add the 2y dx, or plus 2y times dy dx. And dy dx is a common factor to both of these terms. So rewriting it a little bit, 5 minus 2y is equal to the quantity 2x plus 2y times dy dx. And again, you probably already picked up on where this is going. We're going to end up with this weird looking expression, but a derivative nonetheless. 5 minus 2y divided by the quantity 2x plus 2y is equal to dy dx. That's our derivative. This is our derivative of y with respect to x in terms of x and y. And again, if we had an actual coordinate point somewhere on this graph, we could just substitute in that x and y value, and we would actually get a value of a number that's a slope. Other than something where x is equal to negative of y and you need 0 in the denominator. That'd be no good. But otherwise, we're doing pretty good. So there's our derivative.